This is the final episode of the Real Analysis Preliminary series. We will state the axiom of choice in Zorn's lemma precisely, and explain that they are equivalent without proving the equivalence. Then Zorn's lemma will produce a basis for an arbitrary vector space, because apparently even existence needs paperwork. For finitely many non-empty sets, choosing one element from each requires no new axiom. Ordinary induction handles it. The problem concerns an arbitrary indexed family, possibly uncountable, with no preferred element in any member set. We want one simultaneous choice from every set, not a separate promise that each individual choice could be made someday. Here is the precise statement. Let X sub I, indexed by I in I, be a family of non-empty sets. The axiom of choice says there exists a function f on I such that f of I belongs to X sub I for every index I. The function f is called a choice function. If a canonical rule already defines f, no axiom is needed. Choice matters precisely when existence outruns description. A choice function is exactly an element of the Cartesian product of the family. Thus choice is equivalently the statement that a product of non-empty sets is non-empty. Finite choice is a theorem of ordinary set theory. Countable choice is weaker, while arbitrary families require the full axiom. These distinctions matter whenever a proof casually says choose one object for every index and then changes the subject. Zorn's lemma lives in a partially ordered set, a set with a reflexive, antisymmetric, and transitive relation. A chain is a subset in which every two elements are comparable. The entire poset need not be linearly ordered. An upper bound of a chain C is an element U of P lying above every member of C. The upper bound need not belong to the chain itself. Requiring that would be a different theorem, which is how definitions retaliate. Zorn's lemma says, let P be a non-empty partially ordered set, and suppose every chain in P has an upper bound in P. Then P contains a maximal element. The proof pattern is therefore clear. Design a poset, verify chain upper bounds, and receive a maximal object. Of course, designing the correct poset and verifying the hypothesis is where the mathematics was hiding. A maximal element has no strictly larger element above it. A greatest element lies above every element of the poset. For example, under inclusion the two singleton sets shown are both maximal, but neither contains the other. So the poset has two maximal elements and no greatest element. Zorn guarantees maximality, not universal domination. English reused similar words, and mathematics declined to intervene. Over ZF set theory, the axiom of choice, Zorn's lemma, and the well-ordering theorem are equivalent. Each can be proved from either of the others, so adopting one gives all three. We will not prove those equivalences here. They deserve a separate treatment rather than a decorative arrow and suspicious confidence. Let V be an arbitrary vector space over a field F with no finite dimensional assumption. Here basis means Ha-Mel basis, a linearly independent subset B whose span is all of V. Every vector must be a finite linear combination of members of B. This is not a Schauder or Hilbert space basis. Some spaces have an explicit basis. The theorem concerns an arbitrary vector space, where no useful list may be available. Let P be the collection of all linearly independent subsets of V, ordered by inclusion. This poset is non-empty because the empty set is linearly independent. A maximal element of P is therefore a linearly independent set that cannot be enlarged while remaining independent. To invoke Zorn, we must now prove that every chain in this poset has an upper bound inside the poset. Take any chain C of linearly independent subsets, ordered by inclusion. Let U be the union of every set in the chain. Each member of the chain is contained in U. So U will be an upper bound in P once we prove that U itself is linearly independent. A union of arbitrary independent sets need not be independent. The chain condition is doing the actual work. Take finitely many vectors U sub 1 through U sub n from U, satisfying a linear relation. For each vector, choose a chain member S sub I containing it. Only finitely many choices occur here. A finite collection inside a chain has a largest member under inclusion. So 1 S sub j contains every chosen vector. Since S sub j is linearly independent, every coefficient is 0. Therefore U is linearly independent. Thus U belongs to P and is an upper bound of the chain, exactly as Zorn requires. The poset is nonempty, and every chain has an upper bound given by its union. Zorn's lemma therefore gives a maximal linearly independent subset B of V. Maximality means no proper superset of B inside V remains linearly independent. We still must prove that B spans V. Zorn did not include complementary spanning with the maximality package. Suppose some vector V lies outside the span of B. Consider a finite linear relation involving V and members of B. If the coefficient of V were non-zero, solving for V would place it in the span of B, contradicting our assumption. So that coefficient is 0, and independence of B forces every remaining coefficient to be 0. Hence B union V is independent, contradicting maximality. Therefore B spans V and is a basis. In finite-dimensional linear algebra, one can reduce a finite spanning list to a basis by finite elimination. For an arbitrary infinite-dimensional space, that termination argument disappears, and the general basis theorem uses choice. In fact, over ZF, the statement that every vector space has a basis is equivalent to the axiom of choice. Our linear algebra series therefore stayed finite-dimensional, avoiding dependence on an axiom we had not yet introduced. The axiom of choice will return in the real analysis advanced series when we construct a non-measurable set. On the interval 0 to 1, declare x equivalent to y when x minus y is rational. The equivalence classes form a family of nonempty sets. Choice selects one representative from every class. The resulting representative set is a V-Tali set and it cannot be Lebesgue measurable. We will prove that later, after measure has been defined and can properly object to what choice just created. The basic real analysis series will rarely invoke the full axiom of choice explicitly. On the real line, many apparent selections can be made canonical using rational approximations or the least admissible index. So the next 50 convergence proofs are not secretly powered by Zorn's lemma. We include choice here for foundational literacy and because later algebra, topology, and advanced analysis genuinely use it. The axiom of choice provides simultaneous selections from arbitrary nonempty families. Its equivalent form, Zorn's lemma, converts chain upper bounds into maximal objects. That machinery proves every vector space has a Ha-Mel basis and later helps construct a V-Tali set. With that, the real analysis preliminary series is complete. The foundations have finally finished introducing themselves.